Hello everyone, let's begin a new lesson. In this lesson, we continue to introduce the learning program model, and we focus on section 3, typical examples. The vocabulary of learning program is very widely used. In this section, we begin broaden our horizon as you study the following examples. Note that it is their underlying mathematical model rather than their context that characterize them as learning program problems. These examples are scaled-down version of actual application. Now we see example 1. Design of radiation therapy. Mary has been diagnosed having a cancer at very advanced stage. Especially, he has a larger malignant tumor in the blood area. She will receive the most advanced medical care available to give her very possible chance for survival. This care will include extensive radiation therapy. Radiation therapy involves using an external beam treatment machine to pass ionizing radiation throughout patient's body, damaging both cancerous and healthy tissues. Normally, several beams are administered from different angles in two-dimensional plane. Due to attention, each beam diverts more radiation to the tissue near the entry point than to tissue near to the exit point. Scatter also causes some delivery of radiation to tissue outside the direct path of the beam. Because tumor cells are typically microscopically interspread among healthy cells, the radiation dosage throughout the tumor range must be large enough to kill the malignant cells, which are slightly more sensitive, yet small enough to spread health. That is, this is beam 1, beam 2, and this is the tumor cancers, and this is cracked cells, and 3 is health cells. And the information of this problem listed in this table. We must keep health autonomy, minimize killed, and the cracked tissue must less than or equal to 2.7. Tumor range, the tumor range can equal to 6, and the center of tumor must, as possible as many to killed, and then it's greater than or equal to 6. The goal of the design is to select a combination of beams to use, and the intensity of each one to generate the best possible dose distribution. So we analyze in this problem to formulation a learning program. The two decision variables x1 and x2 represent the dose at entry point for beam 1 and beam 2. And the objective function is minimize the health autonomy. We described Z equal to 1.4 x1 plus 1.5 x2. That is, use this low number 2 times decision variables. And the constraint in this problem is critical tissue must less than or equal to tumor range must equal to 6, and center of tumor must greater than or equal to 6. So we describe the constraint in these critical equations. And the last is non-negativity constraints. And this is the linear model of this problem. Now we see example 2, controlling air pollution. The Netherlands Corporation, one of the major producers of steel in its part of the world, is located in the city of Amsterdam and the only large employer there. Amsterdam has grown and prospered along with the company, which now employs nearly 15,000 residents. But uncontrolled air pollution from the company furnace in uranium, the appearance of the city, and endangers the health of its residents. The directors are discussing what to do about air pollution. The three main types of pollutants in these ashes are particulate matter, sulfur oxides, and hydrocarbons. The new standard required that the company reduce the annual emission of these pollutants by amounts shown in the following table. And in this table, we noticed this is the three pollutants: particulates, sulfur oxides, hydrocarbons, and it is required reduction in annual emission rates. That is, particulates must reduce 6 million pounds a year, and the sulfur oxide is 115 must reduce the emission, and the hydrocarbons must reduce the emission is 125. In both cases, the engineer has decided that the most effective types of abandonment method are: number 1, increasing the height of the smokestacks using filter device, including gas traps in the smokestacks. And the 3 method is including cleaner, high-grade materials among the fuels of the furnace. Each of these methods has a technological limit on how heavily it can be used. For example, a maximum feasible increase in the height of the smokestacks. But there also is a considerable flexibility for using the method at a fraction of its technological limit. The following table shows how much emission can be limited from each type of furnace by fully using any abandonment method to its technological limit. That is, we notice in this table, we can install the smokestacks in blast furnace, open hearth furnace. We can use filters in blast furnace, open hearth furnace. We can use bed fuels in blast furnace, open hearth furnace. It can reduce the emission or decrease the emission. Particulates is 12 million pounds, 9 million pounds, 25 and 20 and so on. A method annual cost includes increased opening and maintenance expense as well as reduced revenue due to any loss in the efficiency of production process caused by using the method. The other major cost is start-up cost required to install the method. The total annual cost estimates in millions of dollars are given in the following table for using method at their full abatement capacity. That is, in this table, install taller smokestacks of blast furnace may be cost $8 million. If installed in open hearth furnace, maybe cost $10 million. Filters used in blast furnace maybe cost $7 million each year. Filters used in open heat furnace maybe cost $6 million, and so on. Now, in this problem, we have the question. This problem specified which types of abatement method will be used, at what fraction of their abatement capacity. For 1, the blast furnace, and 2, the open heat furnace, the requirements with the smallest possible cost. Now, with formulation of this problem, first to determine the decision variables. The decision variable is to determine which fraction use 3 methods in two furnaces. So we set X1 means taller smokestacks used in blast furnace. X2 means taller smokestacks used in open heat furnace. X3 means filter in blast furnace. X4 means filter in open heat furnace. X5 and X6 is backfills in blast furnace or open heat furnace. This is the decision variable in this problem. And step 2 is to determine objective function. Objective function is minimize the cost each year. And we know in this table, the table is the cost of in this table. This number is expressed the cost. Use these 3 methods to these 2 furnaces cost each year. So we time these numbers to time decision variables. So we describe objective functions. Minimize J equals 8x1 plus 10x2, 7x3 plus 6x4 plus 11x5 plus 9x6. Step 2. We think about the constraints in these problems. In these problems, the constraint is the reduced emission pollutant must satisfy the annual reduced. So we see in these problems, the particulate reduced is X1, X2, X3, X4, X5, X6. So particulate reduced each year is 12x1 plus 9x2 plus 25x3 plus 20x4 plus 7x5 plus 13x6 much greater than or equal to each year. Emission reduction is 16 million pounds. On the sulfur oxide, we use this low number 2 times decision variables. This is the left of these constraints, greater than or equal to 115, and this is in each year emission reduction. And the hydrocarbons use low number 2 times decision variables. We get this expression much greater than or equal to 125 million pounds. And in these problems, x1, x2, x3, x5, x6, the decision variable is a fraction of installed 3 methods. So the technological limit is xj less than or equal to 1. 1 means 100%. So this is the model of these questions. Now we introduce example 3, requirements solid waste. The sewage company operates a reclamation center that collects 4 types of solid waste materials and treats them so that they can be regimented into a saleable product. 3 different grades of these products can be made depending upon the mix of the materials used, although there is some flexibility in the mix for each of the proportion of material in the product grade. For each of the 2 higher grades, the fixed percentage is specified for one of the materials. The information of grade product specification is in this table. Grade A products, its specification is material 1 not more than 13%, material 2 not less than 14%, material 3 not more than 15%, material 4 exactly 20%, and similar to grade B product, grade C product. Grade C product, only one specification, material 1 not more than 70 of the total. And this column number is the cost per pound of grade of product. And this column number is the selling price of each product. And we can use this number minus this. That is 8.5 minus 3 equal 5 is the profit of grade A product, each product. The reclamation center collects its solid waste materials from regular resource, and so is normally able to maintain a steady rate for treat them. The solid waste materials information is listed in this table. Material 1, 2, 3, 4. Pounds per week available is 3,000, 2,000, 4,000, and 1,000. Treatment cost per pound is $3 of material 1, $6 material 2, $4 material 3, and so on. And additional restrictions in this problem is for each of materials at each of the pounds per week available should be collected and treated. That is, a half of this is must treated. And the restriction 2 is $13,000 per week should be used to treat these materials. The sewage corporation is solely owned by Green Ells. Green Ells has raised contribution and grants amount $13,000 per week to be used exclusively to cover the entire treatment cost for the solid waste materials. The board of directors of Green Ells has instructed the manager of sewage to divide this money among the materials in such a way that at least half of the amount available of each material is actually collected and retreated. So in this problem, our question is, management wants to determine the amount of each product grade to produce and the exact mix of materials, to be used for each grade so as to maximize the total weekly profit. This is the question. we analyze these problems. Step 1, to determine the decision variables. The decision variable is we can produce product grade A means XA, but it is mixed by material 1, material 2, material 3, and material 4. So we set the decision variable is XA1, XA2, XA3, XA4 is pounds of material J allocated to product A. And we set XB1, XB2, B3, B4 is the pounds of material J allocated to product B. And XC1, C2, C3, C4 is the pounds of material J allocated to product C. This is the decision variables. Step 2, determine the objective function. The objective is to maximize the profits. So we describe the maximized profit is grade A product profit, grade B product profit, grade C product profits. And we use this number to minus. That is 8.5 minus 3 is 5.5 times grade A total amount. Grade B profit is 7 minus 2.5 is 4.5 times grade A total number. Grade C profit is use this number to minus this. That is 3.5 times amount of product C. This is the objective function. Step 3, determine the constraints. In this problem, the constraint is more protected too. So we determine two field kinds. The first kind of constraint is mixed specification. Mixed specification in this table. Grade A product, material 1 is no more than 13 of the total. We express the XA1, this is the total, and the divider is 13%. So less than or equal to. Material 2, not less than 14%. XA2 divider, this is the total amount, greater than 14%, and so on, these constraints. This is the specification constraint. And two kinds of constraint is available of materials. And in this table, we notice that the materials of 1, 2, 3, 4 each week is available, this number. So we can express the as this is material 1 is used in producing products, and this is available material 1. This is material 2 used in the proceeding of production. This is available materials, and these 3, 4 is all the available materials. And third kind of constraint is restriction on amount treated. That is, at least half of the pounds per week must be treated. So material 1 used is this amount. Grade 1 half of this 3,000. And the material 2 used in the proceeding must greater than or equal to half of this number, and so on. And the content of this total cost is 13,000. 13,000 is in this problem, we need the cost is 3 minus times material 1, total number, 6 times material 2, material 2 total number, material 3 per pound cost times the material 3 total number, material 4 price times material 4 total number equal to 13,000. And this is the resource constraint. And lastly is negative constraint is Xij greater than or equal to 0. So this is the constraint of these problems. And we summarize the model of this example is this model is very large. It's very large. And constraint is many. So this is the example 3. Now we introduce the last example, example 4, personal scheduling. Union Airways is adding more flights to and from its harbor airport, and so it needs to hire additional customer service agents. However, it is not clear just how many more should be hired. Management recognized the need cost control while also consistently providing a satisfactory level of service to customers. Therefore, an OR team is studying how to schedule the agents to provide the satisfactory service with the smallest personal cost. Based on the new schedule of flights, an analysis has been made of minimum number of customer service agents that need to be on duty at different times of the day to provide a satisfactory level of service. The other entries in this reflect one of the provisions in the company's current contract with the union that represents the customer service agent. The provision is that each agent work an 8 hours shift 5 days per week, and the authorized shift in the following table. In this table, we notice that the shift is 1, 2, 3, 4, or 5, and this is the each shift work time period. 6 a.m. to 8 a.m. shift 1 can work in this period. This period, shift 1 can work in this period, and this period, shift 1 can work in this 4 period, and they have 8 hours. And shift 2 can work in this period, and they are 18 hours too. And we notice shift 5 work from 10 p.m. to 12 p.m., 12 p.m. to 6 p.m., and this is 8 hours too. And the minimum of the agent needed in each period is 6 a.m. to 8 a.m. minimizes 48 agents. 8 a.m. to 10 a.m. need minimize the agent is 79, and so on. And the last row is the daily cost per agent. Shift 1 per agent is $107. Shift 2, $116 per agent, and so on. So in this problem, we analyze the formulation procedure. We set Xj is the number of agents assigned to shift J, because in this problem, we needed to assign the agent to each period and to satisfy the service. The main restrictions on the values of this decision variable are that the number of agents working during each time period must satisfy the minimum requirements. So in this table, the decision variable is x1, x2, x3, x4, x5 is each shift agent assigned to. And the constraint is in this period, x1 can work in this period. So x1 must greater than or equal to 48. 48. That is, the worked agent in this period must greater than equal to minimize agent in this period. And in second period, x1 plus x2 greater than or equal to 79, and so on. And the last period is x5, only x5 can work in this period. So x5 greater than or equal to 15. This is the constraint in this problem. And the objective is the minimized cost. Minimized cost, we can express the 117 x1 plus 116 x2 and so on plus 195 x5. This is the objective function, and this is the minimized cost. So we economize the So we summarize this model of this problem. It's the objective is minimize D, and subject to these constraints, and the xj is equal than 0. So in these lessons, we have introduced 4 examples to tell you how to set up or building up linear problems. Thank you very much.